So welcome to today's webinar. We're going to be looking a little bit, just talking about maths teaching approaches, many of which you will no doubt come across. And then we're going to be doing some maths based on binomial expansion and sequences and series. As you can see. So in terms of teaching approaches, so this is just a little bit of theory that we have at the beginning of each of our things in subject audit enhancement. When you think about teaching approaches, what have you seen? Will?
Quite a variety, to be honest with you. I mean, at the moment, I'm kind of at the end of my placement where the teaching approach is very much dictated by the head of maths' desire to sort of really hammer through the curriculum very, very fast and then spend a lot of time revising. To such an extent, we actually started teaching GCSE in Year 9. They've given up teaching Key Stage 3 for 3 years. Start teaching GCSE in Year 9, finish the syllabus at the end of the second term of Year 10, and then revise for 4 terms before the exam.
Wow.
So it's very much pace-led there. But at King Edward's, there was a great variety. I mean, one of the teachers there was particularly keen on almost sort of minimal instruction in terms of he'd do a quick example on the board and then give his class, which was a top set Year 10 class, tons of stuff to do, and say that this is the 5-6 challenges I want you to achieve today. I think most of you will get to this challenge, and then just run around the class, sort of checking what people that were doing, assessing their learning, and helping out where it was required. And the sort of the very interactive lessons where people are talking about where they're getting lots of like cool toys to play with and sort of learn by discovery almost.
And which one do you think is more effective? Which just looks to be more effective?
The one that sort of seems the most interesting for the students is very much the sort of the certainly with middle ability seems to be the discovery. So we're actually getting them to do things to sort of and then sort of think about the maths involved in doing that. With a high set class, it seemed very much to be, you know, let them get on with it and then sort of help them with any questions they had. But in terms of full exam results, it's actually the one, it's the high pace sort of get everything covered quickly and then revise it, because the school maths at the moment, they've been teaching maths for 6-7 years ever since the head of maths came, and they've been having 80+% C class pass rates at GCSE, which they see continuing. So they're doing, I think it's just literally they become almost an exam factory. So it's at odds with a lot of the sort of what we're taught on course in terms of how we should teach and how they like us to teach. But it is statistically shown to be effective.
I know, and I feel this conflict very strongly because unfortunately, and that's why people are like, well, the way that we did it always worked, because to a certain extent it does, because you're right, it's exam preparation. And I have to admit, I never got as good results in the department as some of the others that did that. So although I had more interesting lessons and a lot of discovery, my results were always just slightly behind. And it's just a bit disappointing, really. But one year, or for a couple of years, I got the kids to fill in questionnaires about other things apart from just the maths performance. And in terms of sort of their skills and their metacognition and their general creativity and problem-solving abilities, it definitely enhanced those. So it depends on whether we are focused on creating drones who can pass GCSE exams versus creating well-rounded individuals who can tackle maths problems as they come across them. Unfortunately, sorry, both.
So yeah, I kind of agree with you, because the thing I've really noticed about that, yeah, okay, the exam results are sparkling at the place where you're just literally going, this is how you do it, this is how you use, go and practice it. But whenever we've tried to experiment a little bit with sort of a new type GCSE syllabus, where there's a lot more problem-solving questions, where you're presented with an odd-looking triangle and you've got to decipher the angle to prove that it's similar or something like that, the kids then are seen far more lost. And whilst you can sort of, with the bright ones at least, sort of show them how to think about it and then pick it up really, really quickly. it's the sort of the ones with the middle ability up there, I think are going to get hit quite hard when they get to these sort of problem solving questions that are going to give them the marks they need to cross the sort of the grade 5 boundary, and they're just not going to have the ability to think around a problem in the way that they'll need to for that. So I think the latest curriculum and the latest sort of syllabuses for the new GCSE and maths is going to actually mean that a more sort of discovery and sort of independent learning type method approach, the type approach to teaching maths is going to reap benefits, and I'd be interested to see what happens in a couple of years' time.
Yeah, here's hoping.
OVHS's results.
Well, yes, and I think, you know, obviously these skills that they learn in maths by doing all this problem solving and having to think outside the box will help them. Well, actually, it's more inside the box logically. Well, and a bit of that. You know, should help them more across their subjects as well, and just be more interesting. I mean, I think we haven't really talked about the low ability ones, but if at the end of the day they're happy to come to maths, that is a major thing. So when they come along and they just sit there and they do the same thing, they don't get it, but they just do it, it's got to be tedious. So there's a lot to be said for, well, a variety of approaches. Trying to combine the two, which I guess is what most of us do, a bit of both. So they're a bit of both. They're halfway there and not really that. But in 1982, they said maths teaching at all levels should include opportunities for teacher talk, so exposition, explanation, questioning, discussion between the teacher and all the students, practical work, consolidation and practice of fundamental skills, problem solving, application of maths to everyday situations, and investigational work. So 1982, that was already coming out. I can't say that I was particularly had much discussion between students. I remember very much sitting individually. Practical work, by that I think they must, you know, have interpreted using my compass to draw a circle, for example. Investigational work didn't happen very much, apart from when we had to do coursework. So, you know, although it has been there, and in fact it's interesting, when you look back through the curriculums, which is what I'm doing at the moment for my dissertation, because I was trying to pick out how things have changed, they haven't. What people have been saying about what maths teaching should be remains the same. But it seems to have taken a really long time to be getting anywhere with more constructivist approaches to teaching. And still, you know, I go into schools and you still see that actually when you talk to a lot of teachers, they are still doing the stand at the board, tell them they do it, get them to practice approach. So you can do a bit of that, but hopefully the constructivist approaches of active learning, inquiry learning, problem-based learning, collaborative working. I was going to say how are these the same, different, but you know, I'll talk about this really so we can move on. The active learning is obviously just getting them up and doing stuff. Inquiry is where you just, you know, give them a prompt and leave them to get on with it. Problem-based, give them the problem. And collaboratives when they're working together. So you can put all of those in together as one thing, or you know, use different bits of that. Just in terms of approaches using ILT, information learning technology, calculators, you know, we do use them, but you know, as we've talked about before, the kids really don't have mastery of their basic calculators. And you could definitely do with more than that. Using software is something that I did a lot at A-level, but less so in GCSE classes. We do sort of things, you know, using websites and finding videos and that sort of thing. But webinars, wikis, I mean, you know, have any of you found that you've used any really new technology in your lessons? Or you've seen anyone using really new technology in their lessons? No. It was hilarious because I remember a couple of years ago, must be about 8 years ago, the chemistry guy going, "Look, I really want to get some tablets," and we were all like, "Ooh, tablets!" And he got one that he could pass around the class, you know. And we all sort of had a go at that, and we were like, "Wow, okay, let's figure out how to use this." And now here we are. It's very everyday, but who is embracing that? I've seen some amazing presentations, actually. I don't know if you guys have had any on your course, where you can use your iPad like a 3D printer, and you hover it with a particular app, or your phones. It's just an app, basically. You hover it over a weird printout, and it makes it, you can see it in 3D when you look through the iPad. It's absolutely amazing. In fact, I've seen them do it for a whole warship, and you can see the whole thing in 3D. So, you know, if the kids had tablets and that app, you could get them all doing, you know, the 3D shapes where they have to do the plan and the elevation and those sort of things. Sorry, I'm sat here with my imaginary tablet now. You know, there's so much more we could be doing. But a lot of the time what happens, it's like they go, okay, well, we'll buy a whole class set of laptops. Oh, look, they never got used. Oh, this technology is a waste of money. So, you know, have a look around and give things a try. Has anyone used the, you know, the QR codes? Has anyone used those as an activity? Oh, I guess, are the kids all not allowed their phones or anything?
Yeah, we do phones out of the classroom.
In sixth form, you see, BYOD, bring your own device, is really big, because there's not much money in sixth form, because it's funded by itself rather than the government, and so we can't just go out and buy tablets for everyone, or not that anyone really can. So we say, well, come on guys, you've all got phones now, download this app and do the QR code scanning. And then, like, for example, for revision, you can type it in and create QR codes for each thing and send them like on a treasure hunt around the room. Well, are you walking somewhere? So you can print out loads of revision ones and have questions, and they can go and scan it with their phone and get answers and various things like that. So that's quite a cool way. But yeah, sadly, if you're not allowed phones and you don't have any technology in the class, well, you know, if you have an iPad yourself, then you can do it to a certain extent with them all crowded round or taking turns. But yeah, it's not very well supported, is it? So when you guys think about teaching, do you think you have you yet developed a certain style? Is there a particular pattern that you like to follow? Anyone want to say what they've been doing? Alex?
Yeah, I think it really, sometimes it depends on, well, it does, it depends on the class, you know, the people that you're talking to. So behaviour control comes into the methods that you choose to teach. So when it was I'm now only teaching year 7 and 8 at the moment, so but year 8's a high ability, so there you can do the exploration and you can set them 3 on tasks. But the year 7 3, they can't even sit in pairs with each other because of bad behavioural problems. So then you end up standing at the board for the majority of the lesson, writing on the board, giving them a question, moving on to the next thing. That old style that everybody's trying to move away from.
Yeah.
It really depends on their ability and unfortunately their behaviour.
Yeah, so the question really is, how do we retain control without having to stand at the front all the time? And I don't know the answer to that. I would be interested if anyone does want to do that as their assignment, if they want to give it a go. But when I talk to the people who have the full, you know, that do inquiry with everyone, obviously you guys have got it different because you don't own your class and haven't started with them. But when you do, you go in and you set up the ground rules, and from the start, they understand that you're all in it together, and you know, you're just not accepting bad behaviour. We're going to go in we work in groups, but if you're getting out of hand, then we go back to the boring. You sit and stand at the board or something. But yeah, I mean, low ability year 7 and 8. Yeah, yeah. I would be interested if anyone wants to do research on that. There's definitely something in that to find out about, because you're absolutely right, and unfortunately that's why it keeps returning endlessly to this standard board to keep them on track. And we did, so I had a lot more freedom in sixth form, because there's some bad behaviour, but you just say, look, if you don't want to be here, just leave, and do. So it's different. I'll investigate that if I can. And Jerry said, the principal's talking about taking computers out of the classroom, so you don't get distracted from what's important. But again, I think people are losing sight of what is important. The year 8 person disrupts that class learning. Brilliant, yeah. Oh, that's a shame. Many of our maths subscriptions cancelled. Yeah. Jerry, were you going to say?
It's shocking. I've left this school now.
Right.
I'm now without a school because I've been shocked at the decision making that our new principal has come in with. I mean, that, taking the phones out of classrooms. I've been there a year. My phone rang 3 times, I think, in that year, and disrupted the lesson for 5 or 6 seconds. What happens now is 2 year 8s are academy hosts they're not allowed to have work sent down because that will stop them from being able to concentrate on errand running. So they lose a whole day. And then
whole day? They're there the whole day?
They're in reception for the whole day, and they do it once a term. And then guess what? When someone needs to send a message, they send one of these runners, they knock at the door and disrupt my lesson.
Oh my God,
in a way
like Victorian
time.
Make
it up. You could not make it up. And this woman, the same woman that came up with that idea, has now said, I don't think you should have computers in the classroom because they're taking your attention away from teaching the kids. So I can't use things like My Maths, Maths Watch, GeoGebra, anything, because that is a distraction and I should be chalking and talking. But get this, you just said about bring your own device.
Yeah.
Our school has a zero tolerance to the girls using their mobile phones in class because of bullying issues and all sorts.
Right.
But she's now said what would be a good idea is if teachers aren't going to have computers, maybe the girls could use their phones in class to do research. Seriously, you cannot fucking make it up. Which is why I've left. I actually quit the course 3 weeks ago over this, and I've been talked into staying on and and
oh my God, right.
And et al. Are trying to find me a new school. But a mini apology. I'm a little bit disenfranchised and
I can imagine. But that's like the dark ages, seriously.
Because my alternative placement has fallen down as well, so I don't know where I'm going after half term.
Right.
So yeah. Sorry, soapbox away now, but you threw in that bit of bait, and I couldn't bite my lip any longer.
Well, no, I can't believe that. I mean,
and I'll now start listening to what you're saying again.
That's all right. Well, I mean, but the people like in English and history or wherever, where they have to do lots of research, what are they not sort of going? Hello, there's no way that kids can do any of this on phones.
Okay. Let me put it. I'll tell you what they're doing. I know Ford confided in me that they're putting the notice in next week.
Right.
3 people have already left, walked out.
Yeah.
This term, including one of the deputy principals who's taken early retirement.
Oh,
so that's what people are doing.
Oh, there's no place for Luddites, is there?
And one of the best teachers in the school, who's one of the people that mentors me for maths, she's not my mentor, she's thinking of leaving, and that the whole department is, well, 2 departments will fall down, maths and EAL, when she goes.
Right.
And that's all one person's influence.
Yeah. Ridiculous.
I've been completely blown away by how ridiculous some of the decision making is, and the sheer magnitude of the impact it's had on the school. Yeah, this woman's been there 2 terms.
Has the, what did Brighton say about that? I mean, is there someone that you can report that to? It seems like a form of
Well, there's
negligence.
Board of Governors that.
Oh yeah.
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 Look, yes, there probably is, but I've been.
It's not your fight. It's not your fight.
I wear my heart on my sleeve. I'm quite forthright. I'm quite strong-willed. But I was told by the university almost a year ago to stop making waves. By making waves, what I assumed they meant was stop pointing out problems and offering solutions.
Right.
So I don't do it anymore.
Okay. Oh well. Hopefully you'll find a new placement where it's all lovely.
Yes.
And you'll be like, oh right, this is what teaching's supposed to be like.
Yeah.
So this, I think this is really, we've talked about this kind of the different styles. So in the US, it's very much like we do. They give an example on the board, they explain, what perimeter was, then explain the area of a rectangle, the pupils do the practice, then how to do triangles, they do the practice, and then they work individually. And a typical Japanese lesson, they just give them a problem, they attempt to solve it, often in groups, then they present back to the class. And this was, I didn't watch much of that, the teaching with Shanghai, but it's the same sort of thing in Shanghai and China, where this is what they're doing. So although it looks like they've got these enormous classes and they're working very intensely doing this, at the end of the day, the pupils are actually having to do presentations, and that's pushing them through Bloom's taxonomy, because it's pushing them up towards, when you can explain something to someone else, you've had to go through all the different stages of learning in order to get there. Whereas here, you can do it all completely passively and not take any of it on board. And yet somehow pass the exams. Very tricky. Hopefully we'll get there. Anyway, there's some references there about various different people. I mean, these guys, I have to say, this piece of work is just laughable. They are, it could have been written by Go. But anyway, it provides an interesting option. Let us get into some maths. Woo! So this is binomial expansion, which is at AS, and it's all about expanding a binomial, which is just 2 things in a bracket. A trinomial would be 3 things in a bracket, for example. So something in a bracket to a power. So we are going to look at how to do this. In terms of why this is useful, because it's very much used to be taught very much, again, just as an algebraic exercise. Look, we want to expand this. So imagine it was 1 plus x to the power of 2. You could just expand that yourself. When it gets to 1 plus x to the power of 17, you don't really want to be multiplying out 17 brackets. So what we're going to be doing is finding a way to do that quicker. Now, the reason that this is useful is, if you imagine, how could you work out 1.1 to the power of 5 without a calculator? Could you do that in fact? So you could think of it as 1.1 times 1.1 times 1.1, and you could do that without a calculator. You could work that out yourself. You could roughly try and figure it out. But you could also think of it as 1 plus 0.1 to the 5. And then this expansion will help you, because when we multiply this out, we end up having a load of things that we can add rather than having to do a lot of multiplication. So, pens at the ready. I'm sure you can do this. Just getting your brains going. Expand the following. Just using your knowledge of expanding brackets. Will, did you do that without a calculator? Yes. Not obviously that one, I meant the one before.
Yeah.
How did you do that?
Well, I expanded it, so it's 1 plus 0.1, and then I just went 1 to the power of 5 is just 1, and a 0.1 to the power 5, so, well, 0.1 is 1 over 10. 10 to the power 5 is 100,000, so it's 1 over 100,000, so it's 1 and 4 zeros and then a 1.
Unfortunately, it doesn't work quite that way, because if you look at what you've just written for the expansion of this,
Yeah.
so, because there's the extra terms, aren't there? You've got the x squared. Where's my thing?
Yeah. Oh, I see what you mean now, yeah.
Yeah. But why am I going to write this? I've clearly written it there. Hang on. Let me just click. I'll just click. So when you expand this, you don't end up just having this bit squared and this bit squared, of course. You've got basically x plus 1 times x plus 1. So you've got x squared plus 1x plus 1x gives you 2x plus 1. Now, expand x plus 1 cubed. So the easiest way is just to take this one and put it next to another bracket of x plus 1. And then expand it. So you end up with x cubed plus 3x squared. Sorry, Will, can you mute your mic, please? Plus 3x plus 1. Now, going on, rather than making you do it, I do make the kids do this, though. I make them go through this process of doing all of these expansions. But we won't spend a lot of time doing that. You end up with 1x to 4 plus 4x to 3 plus 6x squared plus 4x plus 1. Would anyone like to, oh, well, x plus 1, it expanded is just 1x plus 1. Oh. Ow! Whoops, I was going to ask you there before I pressed the next thing. Can you spot a pattern? Who has seen this before?
One of the A-level teachers showed me.
Right, okay. Alex, have you come across, and Adam, or anyone else? Yes, Pascal's triangle, so you've come across it before. Who, well, is that because you saw it on the next slide, or Adam, or if you actually come across it before?
I've seen it before, but I think I've seen it flipped around the other way, maybe. So it's like upside down as opposed to that.
So it's like sideways, yeah.
Yeah. So when I saw this slide afterwards, without all the pluses and the x's in, that made it obvious. But then now I can't unsee it, if that makes sense.
Yeah. Okay. So Pascal's triangle. Yeah. So if we look at the coefficients that are in front of the x's and the ones that are by themselves, we've got 1, so I could put a 1 here because I could do x plus 1 to the naught, which would give me a 1. 1, 1. So the way that Pascal's triangle works is 1 plus 1 is 2. So you're adding the two things to get the next one. There's always the ones going down the sides. So you've got 1 plus 2 is 3, 2 plus 1 is 3. And then here, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So what would the next line of Pascal's triangle be? Yeah, Will?
It'd be 1, it'd be 1, 5, 10, 10, 5, 1.
Yeah, 1, 5, 10, 10, 5, 1. Good, exactly. So that is, right away, we know that we've got the expansion for x plus 1 to the 5. Hang on, I think that's going to happen next. No, it's not. So x plus 1 to the 5 will just be 1x the 5 plus 5x to the 4 plus 10x to the 3 plus 10x to the 2 plus 5x plus 1. So I know that simply by just putting those coefficients from Pascal's triangle in front. So I jumped over this bit. Does that make sense? So Pascal's triangle is related to how we expand binomials. Now here we've just been looking at x plus 1. So when we have x plus 1, we can simply just write out Pascal's triangle and then put it in front of the x's. However, when we have something different, so a and b just represent anything, I've uploaded a sheet called Binomial Sheet, which gets them going through just doing the expansions and figuring out Pascal's triangle. They then have to go through this method, which is what I'm going to show you now. So, to expand 2 plus 3x to the 5 is to the power of 5. Oh, whoops. I'm going to write it all in between them. Annoyingly, I can't seem to get my pen. Am I going to do anything? I can't get my actual pen to work. So, we've got the row of Pascal's triangle. That's what we do first. So we've got 1, 5, 10, 10, 5, 1. So that is the one associated with things to the power of 5. So we know these are going to be my Pascal triangle coefficients. Then I've got to consider what's happening with each one. So when it was 1 plus x, we could simply put them in front of here. Now we've got, effectively, if we can think of it as a and b. So I'm going to go back to this slide, and it says find the appropriate row of Pascal's triangle. So the first two numbers are always 1 and n, and it has n plus 1 terms. So if we need row 6, it's the one with 7 terms, and so we've got 5, we've got 6 terms. So the first term is a, whatever our a is, to the power of n, and then the powers go down, and then the first term has no b in it, but then the powers of b go up. So what that means is a to the power of 5, and then leave a gap, and you'll have a to the power of 4, a to the power of 3, because these basically go down, a to the power of 2, a to the power of 1, and a to the power of 0. Meanwhile, that's what's happening with our a's. Sorry, Will, can you mute your mic again, please? With our b's, I'll put this in brackets, our b's aren't there, because really this is 3x to the naught. Sorry, the power should be now, so there. Then my next one is 3x to the 1. So b to the naught, b to the 1, so the powers are going up. Sorry, my finger is literally going to sleep. 3x to the 4, and so this one now ends with 3x to the 5. Now, as you can see, because the whole thing's symmetrical, it doesn't matter which bit you call A or which bit you call B. And then all I've got to do is write in as well the coefficients for my Pascal's triangle. And each of these terms, if you think about the expansion, when you expand things, they've got pluses in between because, well, actually, always put pluses, and put, if there's a negative sign here, include it with the 3x, so it would be a minus in there with it. So 10, and make sure that the students put brackets around everything so that you don't end up writing like 102, like it looks like I've done there. This is really rather messy, I apologise. Right, and now I can launch straight into this. But instead of having to multiply this out 5 times, I have now just expanded it. It's a bit of a mess, I've still got to sort it out. But doing that would get the students at least 2 marks by showing, well, probably a 3rd mark. So 1 mark for getting the correct row of Pascal's triangle, and then 2 marks for getting it all correct with all the right powers and the coefficients with them. Do you understand what I've done? Is there anyone who's wondering what on earth I'm doing?
So see if the power,
Yeah.
if the power was, I don't know, 15, would you have to write out Pascal's triangle to 15 rows?
We are going to look at that later. Because you're right, they will often do that. In fact, they love to do 20. But what they do is they say, write down the first 4 terms in ascending order, so you don't have to do the whole thing. And there is a way to get the coefficients without writing out the triangle. I would recommend that if it's more than 7, you use the method I'm about to show you to do that, rather than using Pascal's triangle. So Pascal's triangle is great. If you've got to do a whole expansion, the most that they'll ask you in an exam really is going to be 5. Otherwise, they'll just ask for a few terms. Because yes, you're absolutely right. It'd be absurd to have to write it all the way out. I mean, it doesn't take too long to write out Pascal's triangle itself, but obviously to do a whole expansion would take you ages. However, this was how they used to do it before calculators, basically. You know, if you were trying to work out some massive power of something, you would do this. Anyway, you then work out each of these. So this features on a non-calculator paper. So the kids are expected to be able to figure this out, so that they're expected to know that 2 to the 5 is 32. Anything to the power of 0 is 1, and that's 1, so that's just 32. 2 to the power of 4, no wait, have I done it right? Yeah, 16 times 5 times 3. Yeah, so that's something else. If I could be bothered, I'd work it all out, but I can't because I know that I have written it further down the slide. So they just need to then do a next line, probably showing a bit more, until they eventually get to that. I'm sorry that I've done these as hats instead of using math type. So if you had tried to expand that, and the students often do, they seem to forget that they're in an AS exam and that they know how to use binomial expansion, or possibly because they don't know how to use it. And they end up trying to expand that themselves, and it takes them ages, and they get muddled. So that's what they're supposed to be getting. Now, often, instead of asking you to do the whole expansion, it can ask for a few terms, or it may just ask you to write down the coefficients. Now, there's 2 coefficients. Do you see? There's the Pascal triangle ones that we were talking about, which are called the binomial coefficients. And then there's the actual coefficient that you end up with at the end. When they are asked in the exam to, for example, give the coefficient of the x to the 4 term, they're looking for the answer 810. A lot of the students will give the answer 5, or you know, some combination in between. So just to be aware that unfortunately the word coefficients is used to represent the binomial coefficients and the final one. So you're absolutely right, as I put, beyond powers of 6 or 7, it's really tedious. So there is a formula. You can explain it to them or just tell them what it is. I've done it both ways. The one with the explaining is quite fun. It involves them sort of sorting and stuff. Sort of how many ways can you do this? It comes from the number of ways of doing this, permutations and combinations, which we will do at some point. But I've written it all up, and that's the binomial counters sheet. So that's the sort of the more active way of doing it. The formula is given in the A-level booklets generally, but often the students just think, oh, you know, like they don't do something, oh, okay, that's fine, it's in the formula booklet, so I don't really need to know binomial. I'll just get to the exam. They look in there and they have not got a clue what is going on, because it's all written obviously just in A's and B's and X's, and they don't know how to use it. So it's really important that the formula either is explained to them from, you know, the one that's in the booklet to show them what each bit means, or that they can just do it without looking at the formula. I tell them to generally go through the process and forget about the formula booklet. So, have we done, I can't remember where we are at the moment. No, we haven't yet, have we? Did we do any permutations and combinations yet? Have you come across this before? Is that a no for everyone? So that is, oh, okay. N choose 0, N choose 1, and N choose 2 and 0. This is the formula for it. So actually, let's take it a step backwards. What does n factorial mean? What does n with a, that's n factorial. What does that mean?
That's n times n minus 1 times n minus 2 going all the way down to get to 0.
Yeah, so if it was 4 factorial, it would be 4 times 3 times 2 times 1, and so on. So this is looking at n choose r. So what this means when we look at it in statistics, well, it's not statistics, permutations and combinations, this is saying how many ways can I choose r things out of n? And that's what the binomial counter sheet does. It gets you to work through that, getting the kids to pick 3. So for example, you pick 3 counters. They're different. How many ways can you arrange those different counters? So you can have them as 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, and 3, 2, 1. So there are 6 different ways to arrange those 3 counters. So that actually comes from 3 factorial. So 3 factorial is the number, factorial gives the number of ways you can do something. So 3 times 2 times 1 gives us the 6 ways. So the number of ways of then choosing 3 from 4 counters, for example, you've got 4 counters, the number of ways of taking 3 out of them and then arranging them is from this formula. So this is saying you've got your n factorial over whatever ways that you're taking out r factorial, n minus r factorial, times n minus r factorial. So in this case, the r is each power as we're going along. So the r is always the same as the power of x. So just to show you how the formula works, 20 choose 8, 20 factorial over 8 factorial times 12 factorial. That's 20 times 19 times 18. Oh, no, I want to go back there. If we wanted to work that out, especially because it's in a long calculator exam, 20 times 19 times 18, and I have seen kids write this all out, which is very tedious. But I just do dots. And then we've got 8 times 7 times 6, and so on, times 12 times 11, and so on. Now, because of how division works, we can just cross out all of the 12 times so and so on and there. So this is actually going up to, if I pretend that I've got a long, times 13. Everything else after that has been taken out. And then I can cancel as I go along. So 8, so actually I should perhaps have put a few more in here. 17, 16, 15, and 14 can all be cancelled. So 7 goes into 14 twice, 8 goes into 16 twice, obviously this is a quite mess. 6 will go into 18 3 times. 5 will go into 15 3 times. 4 will go into 25 times. 3 will go into 3, I'll cross that one out. 2 will go into one of the 2's. So I'm left with 5 times 19 times 17 times 3 times 13. It's not particularly nice. Still, that's a pretty horrible one. But it's better than the massive thing that we had before. So, using that formula, these basically give us the Pascal triangle coefficients. So Pascal's triangle is just made up of all of these as you go down. So it's like 1, choose 1, 2, choose 1, sorry, 2, choose 0, 2, choose 1. Let me just go back to Pascal's triangle. So, for example, here, anything choose 0 gives you a 1. So this is just, well, let's look at this one. 2, choose 0, 2, choose 1, 2, choose 2. So anything with a 0 or itself is what gives the 1s. And then that's the 1. So then you just got to think that in terms of generating it, you've got to remember the 0 term. So that again looks hideous. This is what it looks like in the formula booklet. And it looks quite complicated, but once we get into the process of doing it, it's easier. And I think now with hindsight showing you this, it's a mistake doing this way around. It'd be much better to show you with numbers first. I don't know what you think, but what's the 08 for, Adam? 08. Or should that be 80? No. What were you typing? Sorry, Adam, was there something that you were typing there? Because you put 08. Is that an
sorry,
answer?
yeah, sorry, I didn't mean to. I didn't mean to do that, sorry.
That's all right.
Sorry, that was me.
That's all right. I just like, oh, I don't know what that means. Okay, that's fine. So this is going on to the next bit. This is definitely a lot more interesting to teach off the webinar, because I would definitely recommend doing it with the counters to show them how to get all this. But also, you would have spent a long time getting them just to do the expansion using Pascal's triangle. So you probably spent a whole lesson just introducing them to the notion of expanding things, and that you're using Pascal's triangle. You do a whole lesson just on that before you get into the question, as Alex said, of what do you do if it's bigger? And this is what you do when it's bigger. Now, this little bit here, binomial is also at the very end of A-level in the second year. And you can use this expansion even when n is not positive, but it doesn't come up in AS level. That's just to show that then means the expansion is infinite. So when it's negative, they're obviously not going to ask you for the whole expansion. So it's infinite, they'll just ask you for the first 3 terms. So, using the binomial expansion, can you write down the first 4 terms of this? So I will do this to show you. Have I done it? Yes. So, the first one is the 1. In fact, I'm going to do a bit before that. I'm going to write each of the bits. So my first one would be 9, choose 0. That's my Pascal triangle coefficient, my binomial coefficient. So basically my 1. And then I'd have 1 to the power of 9 and x to the power of 0. Then the next one will be 9, choose 1, 1 to the power of 8, x to the power of 1. So this x power is always the same as this r. And then 9, choose, how many do I need? 4. Choose 2, 1 to the 7, x squared, and 9, choose 3, 1 to the 6, and x, 2, 3, 4. As you can imagine, typical mistakes involve forgetting as you're going along which one's going down and which one's going out, and switching them, or just generally getting it wrong in the first place, so that you've just got them back to front. Very easy to do. So just got to be really careful. So all of that becomes 1. Here you can see 9 choose 1 is just 9. 1 is just 1 and x to the 1, so that's 9x. 9 choose 2, 1 to the 7 and x to the 1. X to the 3, that's just my writing. So 9 choose 2 means 9 factorial. In fact, you do another line in here. 9 factorial over 2 factorial, 7 factorial. Because, just to remind you, n choose r is n factorial. So that is the key thing the students have to learn or know how to find in the formula booklet, because it's in the formula booklet, but they seem to forget. So 9 factorial over 2 factorial, 7 factorial is this. 9 times 8 times 7, this one, sorry, 9 times 8. It cancels all the 7s because it's got 9 times 8 times 7 times 6 and so on. And we've already got 7 times 6, they've just cancelled those, leaving me with 2 factorial. Same again with 3 factorial. And then they've just worked those out simply. Are there any questions about that? Okay. So I want you guys to have a go at doing this one. First 4 terms. Keep the minus in with the bracket with the minus 3x. And have a go at doing that expansion, please. I'm just going to get up and walk around on my back. Put your hand up on the thing when you've done that. away, go away. Hello? And the fourth term, Alex? It takes, so as you can see, it takes a long time. And you imagine these are kids and they have, like, you know, concentration of a gnat. Takes this takes them a long time, and because you do it for maybe 3 lessons in total, and then you know, they don't come back to it till the exams and stuff. They're ever so slow at doing it, and a lot of them never really get it. So you definitely want to spend a lot of time at the beginning just getting them expanding brackets so they understand what they're trying to, you know, what is this formula for. It is a quick way of expanding. So yes, let's see. Oh, I've got 945. Have I done that? Let's do it. So 7, 6, 5, minus 3 cubed. No, that is 945. 3, 7, yeah, you should have. Yeah, you've got double that, haven't you?
Yeah, I divided by 2 factors.
Oh yeah. Okay. Sorry. Yeah, very easy actually to divide by 3 instead of 3 factorial. I think that's probably a fairly common mistake. So yes, so part of teaching this, as well as trying to get them to explain what they're doing, is to get them to take care and to show as much as they can. And so I like to see this. In fact, they get marks for doing that by showing these C's. If they've jumped straight to this and they've made a mistake, they won't get any marks. So it's worth showing those. And I mean, I had one kid who was able to do this in his head. Really weird. And he would just straight away write it down. But not showing any working, you know, well, you know the risks. So yeah, lots of practice. And then in terms of the questions will be 4 or 5 marks for doing this. So split into seeing the binomial coefficients correctly, getting the powers correct, and then working them out and getting it all correct. So that'd be probably 4 marks in total. Then it might have another little bit to it, which is all about how it was used. So if you're looking to find the value of 0.97 to the power of 4, we could think of it as expanding 1 minus, what are we going to do, x? Yeah, so 0.97 to the power of 4 is the same as 1 minus 0.03 to the power of 4. So if we think about 1 minus x to the power of 4 and expand that just to get its binomial expansion like that, we know that x is 0.03, much easier to put this into there and do 0.03 to get that. I mean, I say much easier, obviously. Well, yeah, there's still some time taken with doing these ones. However, they wouldn't ask them that in an exam. There'd only be the expectation that they could maybe square something, you know, by timesing it by itself. And actually, if you do this calculation, if you just do the 0.03 squared times 6 plus the 4 times 0.03, no, I want to minus that. Whoops. So here, from these ones, if you just do this bit, it actually is quite far away, but often you only have to do the first 3 terms, and then these are so tiny, they don't actually make very much difference to this. So, as I've said, check it on the calculator. Do you get 0.97, in fact, to the power of 4? It's exactly the same. Sorry. So I don't mean to say at what level of accuracy do the answers agree. I'm thinking about at what point going along here, how far do you have to expand it? That's the question. And that's why they only ever really ask for the first 4 terms of the expansion. Because beyond that, the terms are getting so tiny, they're not making much of a difference. So obviously at the beginning it's just 1. If I take away 4 times 0.03, I've got 0.88 already. So I've got 0.88 right away. So to 2 decimal places, well, actually with the rounding, definitely to 1 decimal place, it still agrees. I then add the next bit, 0.8854. So already I'm now at 3 decimal places, I agree. So just doing those 3, which the kids can definitely work out themselves, gives you enough accuracy because not many people tend to work past 3 decimal places anyway. So they are often asked that sort of thing. Any questions about the binomial expansion? My advice is to just go away, do a bit of practice, and just get used to it. It took me quite a few years I think a couple of years of teaching it before I actually had those formulae in my brain. So now they're there the whole time. But I remember teaching it the first 2 years, having to go back and keep checking how to do it. Even though I had done it at school, I just totally forgot. Right, let us take a 5-minute break. And then we will look at sequences and series afterwards. So is 5 minutes enough, or do you want a bit longer? Okay, 10. Yep, have a 10-minute break then. I will see you in 10 minutes. Go and have some tea or whatever. See you then. Right. I've just unmuted you, Adam, because you were bizarrely muted. Did you log off and log back in again? Anyway, when you're all back, stick your hand up or say something. Anybody out there?
Hello.
Hello.
I missed some of that stuff, just what we were just doing, like about 3 seconds worth, well, maybe about a minute's worth of it when I typed 08 because we're letting dogs out, and I am completely lost. I'll have to watch back over the recording of it.
How far back there?
The C stuff, I don't understand that C stuff, so 9C0.
Yeah. Okay.
Which made me lose everything.
Yeah. Well, absolutely. So the C bit, well, and the students do the same. Do you know? It's like they've switched off for one moment and they completely lost it.
Yeah.
I guess read the binomial counters thing that I have uploaded onto the shared area, but also this formula is just the formula that gives the Pascal triangle coefficients. Basically, that's where that comes from. So you can go through why that is the case, but they don't need to know why. They just need to know that it is. So if we go all the way back to here, then basically this is, so on this one, it's 2 choose 0, 2 choose 1, 2 choose 2, 2 choose 0, 2 choose 1, no, 3, and so on. So that's how you get those. So all we're doing when we've got this bit is, instead of writing down the Pascal triangle coefficients, we write each of these down. So you go along going, the first coefficient will be 9 choose 0, then 9 choose 1, then 9 choose 2. I'm saying choose because really that's what the C stands for, but you can just say 9C0, 9C1. So it's exactly the same, the expansion bit's the same. All this does is gets you the Pascal triangle coefficient.
Okay.
So that's what we were then doing there.
Right.
And again. Right.
Okay. Thank you. Sorry for taking a bit of time.
No, it's fine. Is everyone else back is the question. Is anyone else back? Okay. And
I'm back.
still back. So it's just Jerry. Like back twice. Okay, well, we'll get started. Sequences and series obviously sequences are something that they have to do at GCSE, and they will have come across a lot of these ideas, but just not had any sort of official formal definitions given for them. So they might understand what you're talking about in terms of seeing the numbers and figuring out what the sequence is. But reading a question at AS level which says find the arithmetic progression, it is another kettle of fish really. So there's a lot of language that goes in with this. So they are expected to understand the idea of a sequence of terms. I think that's fine. Use definitions and relations. So this, well, we're going to talk about this in a minute actually. Rather than go through it here, I'll go through it all step by step. We won't spend time doing this because I don't. It's rather tricky over webinar, and you know, but it's just an idea to do with your class. You can just give them a load of numbers, ask them to put together some sequences, and swap them with their partners and get them to figure out what the pattern was. And initially they won't be very inventive. You know, they might just be like 1, 4, 6. Could be that you're adding 3 and then you're adding 2 and the next one would be 7, so on. So you could you just have to be able to get them to describe some sort of pattern. So I won't do that now, but that's quite a good way just to get them thinking about it. And also because a lot of the time with sequences and series, with sequences, they're just sort of adding on the same thing. So this has got some really weird numbers, and in fact there's a load of sheets, I think I've uploaded them, or you can just make up loads of numbers. Because they're weird numbers, they can just put them together. There were more numbers that came with this, and get them to come up with really unusual things. So they ended up like timesing it by 2 times 3 cubed, plus, you know, they'll like to find the most complicated things they could possibly do. Equally, they could just make them up completely and swap them with the person next to them and see if they can figure it out. So that's kind of your starter for sequences, just that sort of thing. Now, there are 2 ways at AS that they describe series. I'm talking about series and sequences, and we use the term interchangeably. But a sequence is basically just as you've always seen it, you know, normally separated by commas, for example. That is a sequence. When you start to add those together, so when you add the terms of a sequence, it becomes a series. So when we are at AS level, we tend to use the word series because more often than not, we're going to be wanting to sum them for some reason. So when it then says the sum of the series, what it's talking about is the total of a particular number of terms in the series. So when we're talking about a deductive definition, that is the traditional nth term, just as the students will have done at school. That's generally the one that we come to probably second, because we generally start with an inductive definition. Just as I did here, I simply was adding 4 each time to get the next one. So in the inductive definition, you get the next term from the previous term. So we just look at this, un plus 1, so that means the n plus 1th term, the next term, is the previous term plus 3. So for this one that I've written up here, the inductive definition would just be the next term, un plus 1, is the previous term, or the term we have, plus 4. So that's the inductive definition. So they're expected to know this vocabulary because it will say find the inductive and deductive definition for a sequence or series. So this one's a bit annoying because you can only get to it from the previous one. So it's not as practical as the nth term, which is just the same as, you know, they did a GCSE. So at GCSE, they tend to look for the differences, don't they? So they know the difference between each of these is 4, and so on, blah, blah, blah. So if we then take 4 away from that, the previous term there will be -1. So we know that it'll be 4n. Oh gosh, that's not supposed to be a subscript. I'm sorry, I know it looks like it, but it's not. It's just that my stick down there. So un, the nth term, is 4n minus 1. No, it's not. Yes, it is. Sorry. I was thinking I'd start at 7. No, I'd start at 3. So 4 times 1 is 4, minus 1 is 3. So they can check that, give them any term. So then if they are asked for the 5th term, from the inductive definition they need to just add 4. From the deductive, they know that they have to do 4 times 5 is 20, minus 1 gives them 19. So once you've sort of introduced that to them, they'll be like, well, of course, we've always talked about terms, and we know how to get it from the previous term. So it's just about vocabulary. They can then go back to the sequences that you got them to make earlier and say, okay, so can you, describe yours? Because there'll be a lot that like this, and they will probably have done it like that, where it's really complicated, and they cannot find the nth term for it, because they can currently only find an nth term if they can spot a regular difference, can't they? There's the odd one they could spot, like n squared, or n cubed, things where it follows a familiar pattern. But if you were, doing something really weird to the previous term each time, you're unlikely to be able to spot the nth term. And they're not expected to, if it was something really weird. So here would just be, there's another, so I've uploaded a load of things. There's loads of different activities that just get them investigating different things. One of the things they get really hung up about, and I'm sure you'll know this, letters, the letters that we use. Traditionally, U is used, so bizarrely U with a subset N is used, or A with a subscript K is used. Those are popular notation for series, but you can use absolutely anything. So A, subscript N, B, C, whatever you want to call them. Try not to let them get too hung up, because in the exam it could be called absolutely anything. It's not going to be called N subscript N, though. I can say that. That would just be ridiculously confusing. So, they would never be expected to come up with these nth terms, because they're very bizarre, but they might use them to get them. And sometimes they're given an inductive definition like this, then that gets them to write out a few terms, and then they can discover the deductive definition. They are also, and actually, as you can see, there's a lot of vocabulary here. They're expected to be able to recognise and describe the behaviour of a sequence. So a sequence is convergent if it gets closer and closer to a particular limit. So if we think about, can anyone give me an example actually rather than me? Can anyone give me an example of the convergent sequence?
Like 1 over x to the n, or 1 over n.
Yeah. So
when
yeah.
it goes up, it's going to get closer and closer to 0.
Yeah. So really often it's ones that involve fractions. Although I could start it here. So for example, so here I'm dividing by 2 each time. And I continue dividing 2 and it gets closer and closer and closer and closer and smaller and smaller and smaller till 0. Obviously, it's never going to actually get there. It's just going to get infinitesimally small. But that is a convergent sequence. A divergent one, more common, obviously. If you're just adding a number and you go on and on and on, then it won't converge to a limit. Periodic is if it repeats. And so on. So that has a period of 3 because it has 3 before it repeats. And a term is oscillating if it goes up and down around, if the terms lie above and below a middle value. So again, that could just go to 1, 0, -1, -2, and then up the other way again, -1, 0, so it's just sort of, as it sounds, oscillating. It may not be that precise, but it's because often something is oscillating and convergent. If you think about, I don't know, setting off a sound, it's a wave, isn't it? A sound wave. And as it gets quieter, it's oscillating. So if you were to show that as a sequence showing the peaks and troughs, it would be an oscillating and convergent sequence. And it can be quite useful actually to get the students to understand, visual representations of this. Another typical one, so you bounce a ball. That's one that they like to do actually. If you think about dropping a ball, so it bounces up and it's losing momentum all the time and losing height. So again, you've got a sort of oscillating and convergent sequence there. Again, so just more ideas to use with the kids, exploring the inductive definition, gets them used to. So the previous one was deductive, this one's the inductive. They seem to remember nth term and then previous term, but the words inductive. So you can get them to just keep trying lots of those. Typical sort of question. Again, so this one's using K, a subscript K. You've been given the nth term here. So it says it's defined deductively. And the more that the kids see this, and because they'll know that's an nth term because it's not in the previous one, it's saying put in each position and you'll get the sequence. So they just need to do that. So if you have a go at doing that, just before you do that, do you know what this means? Oh, whoops. Let me click.
It's the sum of all terms.
Yeah.
In K equals 1 and K equals 6.
Yeah. So again, this is now sigma notation and is another thing that they're expected to know. Now, I think this can come up at GCSE, or I think it is. I haven't taught sequence in the series at GCSE yet. It may just be something that you show the higher guys, but it's not exactly tricky. It's just a note. It's just because it's a symbol that represents the sum of all the terms from the first term to the sixth term. So really, this is quite nice because you have to find the first 6 terms. So if you find the first 6 terms and evaluate that, do have a go at doing that now. You want this bit explained, Alex, or was that, have I missed? No. What do you need explained? Okay, right. Well, I will do this then. So the first 6 terms of the sequence, you just substitute in each of these. So 3 times 1 is 3, minus 1 is 2, and so on. So substituting in, we get this sequence. Yeah, is that all right? Is it just this bit? Yeah. So this bit, have I typed it? No, I haven't. Right, I'm going to type it. So this means the total of A1, because you put in when K is 1. So you put this one in first, and you keep putting them in as the subscript until you reach the top one. So A2, A3, A4, A5, and A6, and we stop there because that's what the top one says. So what that says is the first term plus the second term plus the third term plus the fourth term plus fifth term plus the sixth term. Now that's what you just worked out in the previous question. So you then can then write out what each of those are. So 2 plus 5 plus 8. So putting those together. Does that help? We'll do another example. Okay, we'll do another one. But if you add all those up, it actually gives you 57. So here we go. Here's another one. So here's a sequence where the nth term is -1 to the k. So to write down the first 6 terms, you just have to substitute in 1, and then 2, and then 3, and then 4, and so on. So I want you to do that and see if you can describe its pattern, and then see if you can do this. Now this is written with just a 5 at the top. It's the same as saying k equals 5. You don't have to put it. So have a go at doing that. Yeah, so you don't have to put the k equals 5 at the top, just putting the 5 is sufficient. But I can see that that's quite tricky because you're thinking, what, I go up to 5, but it's talking about the terms, the number of the term. That is what we put on the sigma bit. So, first 6 terms and the pattern. Yes, Alex said periodic. Nicole, were you going to add something?
There's some oscillating sequence.
Yes, it is oscillating and periodic. Because it's going -1, 1, -1, 1, obviously it is repeating with a period of 2. But it's also oscillating around 0. So it is both periodic and oscillating. And when you evaluate the sum from the second term to the third term, what do you get? Yeah, 0. Because 1 minus 1 plus 1 minus 1 just gives you nothing. The way the third bit is written is a bit confusing. What have you guys done? So describe the behaviour of it.
Yeah, I just substituted what we knew in. So
Yeah.
instead of putting -1 to the power k, I just substituted in the ones that I already had.
Yeah. And obviously you've got the same sort of pattern, but
Around 10.
shifted. Yeah, so I now, when I looked at that, I immediately thought, oh, so it's 5 plus 2 AK, so I've now got a deductive definition. I'm just going to click and see what exactly. Oh, right, okay. So describing is then writing out there. We're going to start looking at this bit in a minute, geometric sequence, because they're generally expected to know how to do stuff involving anything generically, like this. Just write down some terms, evaluate something involving sigma, describe the pattern. But there are two particular types of sequences that they're also expected to know a bit more about. So that's a geometric sequence and an arithmetic sequence. An arithmetic sequence is a typical one where you are adding something every time. There is a common difference between each one. A geometric sequence is where you are multiplying or dividing by something each time. So it has a common ratio. So all of those things that we've looked at so far, I've uploaded them to the thing. There's various games, lots of matching. I mean, sequences and series, they find fairly straightforward, and it's very familiar to them, of course. But, you know, what isn't familiar is the language, and it is one of those things, again, where they are given the formula for the geometric and arithmetic formula in the formula booklet, and yet when it comes to the exam, they're completely unable to know how to use them. So whenever you're doing things that involve formula books, formulae which are in the formula books, I would get the books out, get them to find it, get them to use it by looking at the formula there, because that's what they're going to do in the exam, but they'll then have forgotten how what each of the letters mean and get very confused about it. So this is just another way of getting them to write the sequences down, very like just presenting the different numbers. And again, odd one out. So these are just all sorts of ideas you can do. Let's get on to these definitions. Typical sequence. We've got a common difference. Oh, sorry. There you go. What are the inductive and deductive definitions for this sequence? In fact, we pick on someone, Adam. What is the inductive definition?
I'm going to go with adding 5 every time.
Yeah, so un plus 1.
Or is it 5 and minus 2?
No. It's the un plus 1 is un plus 5. That's the inductive.
Right.
And deductive, yeah, is 5n minus 2. Okay, so this is quite a good way, isn't it, to keep them on their toes. Every time you have a sequence, you're like, what are the two definitions? And here I'm going to show you the connection between the two definitions. Because if we look at what's happening, our first term is 3, the next term we add on 5. The next term we add on 5 and 5 again to the original. And then we're adding on 5, 5, 5. So we're adding on 3 lots of 5. So we can generalize this. If we call the first term A, so 3 is A, And the difference between each term is called the common difference, and that's given the letter D. Can you see that we have U1 is A, U2 is A plus D, U3 is A plus 2D, U4 is A plus 3D. We get to what's called an arithmetic sequence, which I've written completely incorrectly there. It should have an E, because we're adding a same constant each time. And the general formula for any, so U1 is A, U2 is A plus D, U3 is A plus 2D. So what we're looking at is UN is A plus N minus 1D. Can you see that? U3 is A plus, this is the N, so 3 minus 1 is 2D. So for any, it's hilarious because a lot of the kids go, why didn't they just tell us that at GCSE? Why did I have to go through finding the differences and going back one step? And then a load of the others then argue, they go, wait, but that was so much easier. Now we have to remember a formula. And you're like, guys, don't worry about it. It's the same thing, okay? It's just, now you have a formula for it. And it's given in the formula booklet. So you can actually stop remembering how to do it. And unfortunately, they then do seem to stop remembering how to do it or what they're doing. But anyway, so that is the formula for finding any nth term. I do think that I was actually shown that at GCSE, and that some people do. But it just depends how far you feel that your class can go, and whether it's strictly necessary. Because having a process to work something out, like we do when we spot the differences and then take it away to get the nth term, means they can do it to every single one. If they can't remember this formula, they can't do anything. However, at AS, if they use the GCSE method, well, in actual fact, they're not generally asked very simple questions like they are at GCSE. They have to know this formula because they're generally given two different terms of the series and asked what's the first term and the common difference. So what they end up having to do is solve this simultaneously, so they need to know this formula. Now, as well as finding a particular term, and this is where they really start to get confused, this finds a particular term, the nth term. The nth term is often called the general term, and for some bizarre reason, in the MEI formula booklets, they've written general term and written this out, and then they've written nth term and written this out. It confuses them every time. I don't know why they've done it. It's exactly the same. They've just done one with a K and one with an N. Often because some people refer to nth term as like the last. So, nth term, general term, it's finding a term. If you want to then add up all of those terms, you are summing the series. So if you wanted to add up all the numbers from 1 to 100, this is quite a good one to give them, just as a little puzzle, a starter, introduction to arithmetic series. Get them to do that. Obviously, you're going to have loads of them trying to do it. Does anyone know what the quick way is to do this? No? No one come across this before? Okay. Nice little trick here. Okay. Yes. Yes, okay, so you do know. Exactly. Add them up in pairs, because 99 and 1 is 100, 98 and 2 is 100, 97 and 3 is 100, and so on. So you end up with all those. Oh, I didn't do it. I left it as well. But that's quite a nice one to get them to figure that out. And that's very important because actually that leads us to the proof of the formula for summing them. So again, more language. It's called the sum of an arithmetic series, or we also use the word progression instead of series. So this is where I was saying this is the sequence, The series is when we put the pluses between it. So if we want the sum of the first 20 terms, you have to work them all out and add them together, which can get a bit tiresome if you've got masses of them. So we need a formula. So this was going back to our first 20 terms of this 3, 8, 13, 18 series. But we could use the 1 to 100, doesn't make a difference. As we are looking at these, I've worked out the 19th and 20th just by putting in the nth term, just to show you. If I do it in reverse order, then absolutely we can gather these in pairs. So adding them together, I then have got 2 sums, and I get a 101 when I add all of them together. I've got 20 terms, because that's how many the S20 was. So I'm going to have 20 times 101. So if I now just want the S20 by itself, I just have to divide by 2. So 20 times 101 divided by 2 is 1010. Much quicker than typing all of those into the exam. Obviously, you can imagine there are many students who will, in an exam, spend a whole load of time doing that. Obviously, they will not get any of the working marks, and they'll be lucky to get the right answer in the end after. They'll just have wasted such an amount of time. So if we now look at this in general terms, this is what we had. A plus A plus B plus A plus 2D and so on. Write it in reverse. Now when we add these together, A plus n minus 1D is going to give me 2 plus n minus 1D. Same again here, 2 plus n minus 1D. So I get 2a plus n minus 1d all the way along. I've got n of those. So I've got n times 2a plus n minus 1d. And I need to divide that all by 2. So the sum of n terms of a series is given by this formula. I think it's really important to show the students this. Start with getting them to sum it up to 100, show them the fact that you do it in pairs, and that is how you derive this formula. Because later, hopefully, that might help them to understand what the formula does. Because they then look at this in the formula booklet and they're like, oh, it's horrible. But it's really not that bad. So here are all the formulae again. The general term. Now, a plus n minus 1d is sometimes called, because it's the last term, because if you think of the nth term being the last term, if it's got an n minus 1, then that's the one, this is the formula for the nth term. So it's the last term. Sometimes it's called an L. And what that means is that in the sum of this that we just come up with, if we take out a plus n minus 1d from here, we're just left with 1a, and the rest of that is called the L, the last term. Both of those are given in the formula booklet, and it's useful, of course, because if you are just simply told the first and the last term, you can find the sum of them, rather than being told the common difference in the first term. If you want to find the number of terms, it's just the last term minus the first term, divided by how many there are, and add 1. That's not really a formula they need to know, it's just kind of common sense, isn't it? You'd hope that they could figure that out pretty fast. So, I want you to have a go. I will write them up here. So the nth term of an arithmetic sequence is a plus n minus 1d. So whenever you're given a sequence, obviously the first thing you've got to do is just figure out what's my a and my d. And then to find the 17th, you're just going to sub in the 17 as well. So have a go at doing that, please. Yeah. And you know, a lot of this comes very naturally to the kids because they're just like, well, hang on, I need to go 17th term, so I'll have a 16 times the difference. So you know, they're very much, they don't realise that they're using the formula when they figure it out themselves. So you can get them just to do that a lot of times before you introduce the formula. So minus 36. If you find that they're getting really het up about putting, because and this is the problem, because their substitution is poor, their algebraic substitution ability is poor. Well, they need to get kicked off your AS course for this. But anyway, you know, you can go back to. I mean, the thing is that at AS, you don't want to be spending a lot of time doing remedial stuff with them when, you know, and unfortunately, you do spend a lot of time doing that. But anyway, so how many terms are there in this sequence? No? Yeah, I've got a calculator, so if you haven't looked at it. And in fact, so you can either, yeah, so I was going to say, if you can't remember the formula, which is the last minus the first over the common difference and add 1, but I have to say I never use that. If you can't remember that, it's always the fact that you could just find the nth term. So from this, you've got 11, well, in fact, from simplicity, you can just say 4n plus 7, can't you? But let's do this one. 11 plus n minus 1 times 4. Oh, so this is where they start to struggle. When you're actually asked to find the actual nth term, then they've got 4n minus 4. They've got the 11 here. So it does seem more complicated, doesn't it, rather than just jumping to 4n plus 7, which you could work out by looking at the differences. You could just make that equal to the last term, couldn't you? And solve it so that 4n is 643 minus 7, 636. Divide that by 4, 8, 1 into 23. No, I'm doing it wrong. Yes, it is 159. Is that right though when I get 660? Oh yes, yes. I've done that. 636 divided by 4. No, that's right. Just want to do divisions there. So Alex, you can either remember this, which is 643 minus 11 over 4, then add 1, or equally, you can just say, okay, and this is very useful for them to know, because should they be given any term in a sequence, they can find which position it's in. But yeah, sorry, they've used the formula. So, I think I'm going to move on. So it's a lot of just basically using the formula and moving between them to find different things. So here you can spot what the common difference is and thus work out what position that is in. And then you know what the nth term is. Sorry, then you know how many terms there are. so you can then add them all together. The first 100 terms, so you've got your n, and you can work out a and d from those and put them into the formula. This is the common sort of question they're asked. They're given that an arithmetic series has 5th term 21, 17th term 69. So write out what you know. You know that the 5th term is a plus n minus 1d, so a plus 4d, which is 21. And you know the 17th term is going to be a plus 16d, 69. Solve them simultaneously. You can find a and d. Now I want to talk about geometric sequences, because the arithmetic ones the kids have come across. That's really the typical ones they're given at GCSE. A geometric, you're multiplying the previous term by a constant, and we call that R, the common ratio. So here, 2 times 3 times 3 times 3, R is 3. So, for this one, what is the, I've just said what the inductive one is. How do you find the deductive definition? Any ideas? Not so straightforward. Will, yeah.
Is it something like 3 times n minus 1? No, it's not brackets n minus 1, so you can multiply the last number.
Yes, it is. So it is, yeah, if you look at it, 2 times 3 to the naught, that's n minus 1. 2 times 3 to the 1, n minus 1 again. So as you can see, yeah, it's a times r to the n minus 1 is the general formula. So if you look at what's happening, when n is 1, sorry, these are the inductive definitions, which get us towards the deductive definition of un, the nth term is a times r to the n minus 1. So 2 times 3 squared, 3 naught, and so on. Yeah. So knowing that is not something that they generally know before. So this is something that is often pretty new to them. Again, given them the formula booklet, they're expected to be able to use that, no problem. So this one, as you can see, if they were given this sequence, it'd be difficult to spot what the pattern was. But again, this is looking at this, thinking, okay, we could break this up into pattern again, 1 times 2, 1 times 2 times 2 times 2 times 2 times 2. So 1 times 2 to the naught, 1 times 2 to the 1, 1 times 2, and so on, is actually generating a sequence. So it would be interesting to get them to sort of use this as a way to see that process again. So geometric series or progression is when you sum the sequences. Looking again at how we get a formula, if we're summing these together, so we get a plus ar squared plus ar cubed and so on. Little trick which, you know, someone realised, if we multiply it by r, so we've got r times Sn, then we've basically multiplied everything by r. We then do this first one minus the second one, so we get, well, it doesn't matter which way around to do it. So we get Sn minus Rsn, and all of these disappear. So you're just left with the A minus AR to the N. Factorise out the A and the Sn, and we can then divide through by the 1 minus R. So this is the formula for the sum of a geometric series. And there are two of them because, as I said, it doesn't matter which order we do it. Either you do this one minus this one, and you get the first one, or you do this one minus this one, and you get the second one. They're both given next to each other in the form of booklet. The kids again get confused about which one they're supposed to use. Well, if they really thought about it and understood, it's nicer to deal with positive numbers, isn't it? So if they've got a common ratio that's smaller than 1, they're better off using this one because you're going to be taking it away from 1. If they've got a common ratio that's larger than 1, they're better off using this one because then it's going to be positive. In addition, with the geometric, having a look at these two series. Here we're going times 3, times 3, times 3, times 3. What's the behaviour of that series? Going back to our definitions about patterns. What's the behaviour of that series? An answer. Alex, I'm going to pick on you. Oh, Will, you can offer an answer because Alex is not very far.
It's a divergence series.
Yeah, exactly.
The first one, and
yeah.
It's like
and
3a to the n minus 1.
Oh yeah, don't worry, you don't have to. Yeah. And the second one, on the other hand, is the opposite. So it's convergent. So here, dividing by 2 every time obviously is the same as multiplying by a half. So here our common ratios are, our common ratio is 3, so it's bigger than 1. Here our common ratio is a half, less than 1. So when your common ratio is between -1 and 1, you end up with a convergent series, which means that it's going to head towards a limit. The sum to infinity is that limit. So this means as n tends towards infinity, so as it gets bigger, the first one diverges. As n tends towards infinity, with the second one it converges. So we can find the sum to infinity. And the formula for that is we get it by looking at the sum of the series. As r to the n, as r is between -1 and 1, as n gets bigger and bigger and bigger, r to the n is going to get smaller and smaller and smaller because it's a fraction. And it's going to get smaller and smaller and smaller, so that we effectively end up with just a 1 on the top there. So the sum to infinity, the formula is a over 1 minus r. So for this second series, 40 plus 20 plus 10 plus 5, what we're saying is, sorry, rather not the limit that it's headed to, because that would be sort of 0, it's the total that we'd get if we were to add all the terms of the sequence, all the terms of the series. So 40 plus 20 plus 10 plus 5 plus 2.5 plus 1.25 and so on, 0.65. Because those ones are getting smaller and smaller and smaller, we basically could say, okay, I've got 60, 70, 75, 77.5, and I am getting nearer and nearer and nearer. The sum, the limit of the sum is 80. And I can work that out by doing 40 over 1 minus r, which is a half. So 40 divided by half is 80. So, one for you, going the other way, if I know the sum to infinity is 5 and a is 3, what is the common ratio? Adam, was that you going to say something, or you thought better?
Yeah, we're gonna, but they're not gonna type it
Oh, okay.
in case everyone else is doing it. But I don't know whether I'm right.
Oh, right.
I just rearranged it and got r equals 2/5, but I don't know whether that's right or not.
That is right. Yeah.
Oh.
When you say, "Oh, I just rearranged it," seems simple enough to us, but as you can imagine, the kids and their rearranging is just dreadful. So yeah, absolutely, just put it into the formula and rearrange it. But at this point, the students are all like freaking out because they can't figure out that they have to just multiply up to get that, and then divide by the 5. And then they might get to there, and then just lose the 1 somewhere, or make it minus or something. So at that point, they start to freak out. So can't seem to rearrange it, but you're absolutely right. So you can, and it's simply 2 fifths. Yeah, that's it. So they might be asked questions like that, where they're told bits and they can rearrange it to find out. But they struggle. They struggle with all of this because they struggle with their algebra, they struggle with their substitution, they struggle with their rearranging. And understanding English words that are used in math. It makes something that's actually quite simple into something a bit trickier. So the general formulae, a r to the n minus 1 is our nth term. A r to the n minus 1 and r over r minus 1 is the sum. Sum to infinity is a over 1 minus r. And they'll often ask when you use that, and you have to say when r is between minus 1 and 1. So have a go at doing this one. Oh yeah, if you haven't got a calculator, so the sequences and series is in the calculator paper. Okay, it would take way too long if they had to do this all by hand. So you know, sorry, it's quite a large number if you haven't got a calculator. So 3 to the power of 6, I can tell you 3 to the power of 6 is 729. So yeah, we don't really want to spend too long. So should have got 5,832. And here is one of the questions, very common, that the students struggle with. So write out what you know. You end up with a simultaneous equations, but not like the students really have seen before. So have a go at it, and then I'll go through it. I'm just going to go out and walk again. How have people got on? Do you know how to solve the... Yeah, okay. Yeah. Okay. Write out what you have. So we know that the third term is AR squared. That's 12. We know that the sixth term is AR to the 5, and that's minus 96. These two, you know when you have normal simultaneous equations, you take one away or add one. In this case, you can divide to get rid of things. So we want to get rid of the A. So if we do 2 divided by 1, we're basically going to get AR for 5 divided by AR for 2. We can cancel out the A's. Oh, if I don't do that. So I get AR to the 5 over AR to 2 is minus 96 divided by 12. The A's cancel, and R to the 5 is 5 R's, divided by R to the 2 means I end up with just 3 R's on the top. Minus 96 divided by 12 is minus 8. So I've got R cubed is minus 8. So the cube root of minus 8 is minus 2. Often students get a bit confused here because they keep thinking, oh, I can't cube root of negative number, but there's negative squared roots. Of course you can with a cube root. You then substitute your minus 2 back in. So there's R cubed minus 8, so R is minus 2. Substitute minus 2 back into, well, doesn't really matter. Maybe the simplest one, I suppose. Minus 2 squared is going to be 4. So 12 divided by 4. No, I've got it the wrong way. Oh, hold on. How do I do it? Minus 2.
Well, if you do it the other way around, so divide equation 1 by equation 2.
Oh yeah, hang on. Sorry. No, no. Okay.
What, so you get an increasing series? And it doesn't. It goes down third and sixth term.
Yeah, you're right. No, no. It's not getting down. It's not getting smaller.
No, you're right. Sorry. Yeah.
Yeah, it's confusing, isn't it? I know exactly what you're thinking because a minus seems like a small number, but the only reason is it's going to flick back, isn't it, between, because we've got a minus there. We're going to get it going, yeah, so sorry, yours wasn't right, was it? A is 3, so we're going 3, and then we'd end up with minus 6, and then 12. Is it going to, yeah, it's a weird oscillating series that goes up and down. It should still be right though if you went the other way, because what you'd get minus, yeah, because it'd be fine to go the other way. You just get R to the minus 3 is minus an 8. See? And then that means 1 over R to the 3 is minus 1 over 8. And if you look at the equivalencies between them or rearrange it, you still get the R is minus 2.
Yeah, I've rearranged them all.
Yeah.
Oh,
So that's fine for you now. Alex, does that make sense to you?
Kind of. I would have to do a bit of practice for that one. So
Well, you know, it's the same for the kids. It's the first time that they see it and they're just like, what? I don't know how to do this. In another way to think about it, you can substitute it into another thing. So you could rearrange it so that A is 12 over r squared, if you prefer, and then substitute that into here. So you've got 12 over r squared times r to the 5 is minus 96. That's why this works. That's doing exactly the same as I've just done with the dividing. And then you can cancel through there and cancel through by 12 again, and we're back to over here. So ultimately, the dividing through is basically jumping over the substitution process, but that is actually what it's doing. But the students struggle and forget this. In the exam, they kind of get to this stage and don't know what to, to get to this stage. That's fine. They would get marks for doing that. And then a lot of them just use trial and error because they can't figure out how to do that bit. Let's see what else I've done. I think I'm going to skip over these two. Again, this is using the sum formula. And all of this, again, it's just about practice and getting to know the formulae. Bring it all in. Find the sum of the terms of the infinite sequence. Because it's saying there's a sum of the terms, but they're getting smaller, we know that the common ratio is going to be less than 1. So they're asking for the sum of sum to infinity. So provided you know your A and your R, you can just sub that in. Oh, that's all. That's all. Sorry, I feel lucky to do those ones. Oh well, I've finished outright. So that's 2 topics we've just done. That would normally take, that would probably be about 3 weeks worth of work in 3 hours, less than 3 hours. So obviously there's a lot more going on there, and you would want to spend time practicing them and working through a lot of those. Adam, did you disappear and come back in again there? Just because you're thinking to go.
No, I was still listening. You were just crackly a little bit.
Oh, right. Okay, that's fine.
Right.
So they're quite nice, sort of little one-off topics. The questions in the exams do get a bit more complicated, I'm afraid. They like to combine them with logarithms so that you end up with this formula, and they're asking you to find n, and you have to take logs, and we'll do logarithms at a later date. Actually, that might be next time. If I find a plan, where's the plan this time? Yes, next time we are going to be looking at logarithms. So I'm talking to you again in November. 20th of November is the next time I'm talking to you. What's that? A couple of weeks after half term. So we will then look at exponentials and logarithms. So a typical question involving sequences and series, they like to do things like trees that grow branches, and every branch grows another 3 branches, and so on. So it grows exponentially. So you end up with an exponential geometric sequence that you then have to use logarithms to solve. So that really, they generally put that as the last question in the exam, and it's a bit of a killer when the kids have spent an hour and a half struggling through the paper as it is. But hopefully most of that has made sense to you. It's all very formula based. So this whole webinar today, you could simply just give the kids the formula and say, go and find out more about this and see if you can do it and get them to do it all themselves. But ultimately it's things that they understand, like expanding brackets and sequences are concepts that they already have. and you're just pushing them a bit further. Any questions about what we've done today? If you had a really high, oh sorry, Will, were you going to say something? I was just going to say, if you have a really high ability class that needs pushing, then obviously because this just takes on sort of the quadratic expansion, the cubic expansion, and sequences, it just pushes it on a bit more. These are sort of things that you could do with them as sort of extension, and there's all of these. All of these different sheets that I've uploaded that have just got questions that you can just throw out to them really for them to have a go at. So I think that is all from me, and I just dawned on me that, did I set you a self-study for calculus and algebra? I think I did. I don't know if anyone's had a go at them. But there were self-studies for calculus and algebra on Student Central, and all of this is on Student Central. But they've reduced the numbers of self-studies you're getting. So your next self-study after those two is not until December. So yeah, so enjoy your half-term break that we've got next. And next time I speak to you will be mid-November. Any questions or anything anyone wants to say?
Thank you.
That's all. Oh, okay. I will put the video. So what happens with the videos? Basically, my computer takes like 3 hours to convert them to the recordings. I'll stop the recording now.